Hey Calculus, this is Mr. Ayton, and this is Unit 5 Review Analytical Applications of Differentiation. And in this video, we're just going to be going over the review exercises. So I hope you had a good spring break. I hope you stayed away from the coronavirus. Mr. Ayton does have some good news, is that I got engaged over spring break. That's pretty awesome. And you can have your own little party by social distancing by yourself in your own home for Mr. Ayton. So what we're going to do is I'm going to go through the Unit 5 review, only the review exercises. Hopefully you've gone through it already. You can take a look to see if you didn't understand something or if you weren't quite sure and you need a little bit more review. This video will help out. Tomorrow go through your sample AP problems for Unit 5, and I will have a video going through each one of the sample AP problems, and you can let me know how you did via email. Would be great. So let's get to this Unit 5 review for calculus. So the first part of Unit 5 review is we're going to be taking a look at the first derivative test. If you remember when we took a look at that first derivative test, what does the first derivative test tell us? It tells us the maximums, it tells us the minimums, it tells us where we're increasing, where we're decreasing, whether there's a slope of the tangent to the curve is positive or negative. It also tells us the velocity. Okay, so as we take a look is when we're increasing, that means the slope of the tangent lines are positive. That's when the f prime of x, the first derivative, is greater than 0. But when we're decreasing, that's when the slope of the tangent lines are negative. That's when the first derivative is less than 0. And so when we take a look at the maximum point, what we're going to do is we're going to take the first derivative, we're going to set it equal to 0, and that's where the slopes turn from positive to negative. That will be when our slopes are positive, then our slopes are negative. That is a maximum point, which means we're going to do the same thing for a minimum. We're going to set it equal to 0, and that's when the negatives go to positives. As the negatives go in the positives, that would be a minimum point. Remember, if we're looking for the overall maximum or minimum, we have to keep in mind the endpoints of a function. And so when we take a look at the second derivative test, the second derivative test tells us inflection points, it tells us concavity, it tells us acceleration. And so this is where the slopes of the tangent lines are going to be increasing. And that's when we're increasing, we're going to be our f prime prime, which means our second derivative, is going to be greater than 0. Concave down is where the slopes of my tangent lines are going to be decreasing, which means the second derivative is going to be less than 0. And how do we know we have an inflection point? Well, we're going to set the second derivative equal to 0, and that is where the concavity ends up switching from concave up to concave down. We call that an inflection point. Okay, so let's do an example problem here. We have a function. That function is y equals 2x cubed minus 3x squared minus 36x plus 2, and we're going to find a. We're going to find the maximum point, the minimum point, the intervals increasing, the intervals decreasing. So the first thing I want to do is take the first derivative, and so I use the power rule. So I have 6x squared minus 6x minus 36. What do we do right here is we're going to factor out a 6. As we factor out a 6, we get 6 times x squared minus x minus 6. And what can we do with that second function? We can obviously factor that guy to become x times x, and we have minus 3, and we have positive 2. And so we have critical points of x is equal to 0. We have x is equal to 2, and those are our critical points. And so what do we want to take a look at? That is an awful straight line. That is very, very, very crooked. So here we go. So here we have our critical point, which means our slopes are equal to 0 at -2. We have a slope is equal to 0 at 3, and we can plug in any number less than 2. And if we plug in any number less than 2 into my original function, I end up getting, into the derivative, I end up getting a positive value, which means my slopes are increasing. And then we plug a 0 in, and we get a negative, and we plug anything bigger than 3, and we get a positive, which means if we're going from positive to negative, that means my max point is right here at x is equal to 2. If I'm going from negative to positive, that means my minimum point is going to be at this x is equal to 3. Did I say positive 2? I meant negative 2 if I got that wrong. And then what are we going to know about our increasing functions? Our increasing functions are going to be from negative infinity all the way to negative 2, as well as from 3 all the way to infinity. Where are we decreasing? We're only decreasing from negative 2 to 3 right there. So that answers A. A told us what our, whether we were increasing, whether we were decreasing, our intervals of increasing and intervals of decreasing, okay, as well as our critical points. So if we go to B, B says find the inflection point in the intervals of concavity. That's a second derivative test. So I'm going to take the second derivative. I'm going to come back up to the 6x squared. That gives me 12x minus 6. Again, I use the power rule. I can factor out a 6, and I get 2x minus 1 right there, which means I have a possible inflection point at x is equal to 1/2. Okay, so what I want to take a look at is I want to take a look at what's happening right here when the second derivative is equal to 0 at 1/2. And if I plug in a point that is less than 1/2, I get a negative value. If I plug in a point that's greater than 1/2, I get a positive value, which means we were concave down all the way. We were concave down from negative infinity, concave down from negative infinity all the way to 1/2. And then we were concave up all the way from 1/2 all the way up to positive infinity, which means I have what is called an inflection point right here at 1/2. And I would be able to construct my graph that way. Okay? So let's move on. We're going to move on to optimization problems. Optimization problems don't come along very often, but usually they're using a calculator. So we're going to draw and label a picture. We're going to write equations. We're going to try to combine equations, take that first derivative test, set it equal to 0, and solve for a variable. So let's get to our problems. So here we have the famous box problem. We're trying to make the famous box with the maximum volume, And so you can see, what do I have here? I have an area times a little height there, so 18 minus 2x squared times x. We distribute that, we get 4x cubed minus 72x squared plus 324. And so what are we going to do? We're going to take our first derivative test because we're doing optimization. We're trying to find out the maximum. So we have 12x squared minus 144x plus 324. And what are we going to do with that first derivative? We're going to set it equals 0. If you plug that in your calculator, use your calculator for this type of problem, set it equal to 0, use that solve function, and we get x is equal to 3 or x is equal to 9. Now if you plug these back in this original function, you can see the 9 does not make any sense. Okay, the 9 does not make any sense. So our x is equal to 3 would be my value for x that would give me the maximum volume, which means if I plug it back in my original function, my volume ends up being 432 inches cubed right there for the maximum volume. Okay, let's go to example number 2. This is another famous example of a river, and we have a fence. We have only so much fence we can use. Our perimeter of fence is going to be 84 equals 2y plus x. We have our equation for area equals x times y, which means I want to solve for one of my values. My x is equal to 84 minus 2y, which means my new equation is area equals x, which we said was 84 minus 2y times y. I can distribute my y right there, and I can solve for x or y. It was just easier solving for x in this problem, which means we have 84y minus 2y squared. We're looking for the maximum area, so we're going to take the first derivative test. We have 84 minus 4y. We can set that equal to 0, and we can easily find my y is going to be 21, which means if my y is 21, I look at my original equation, relationship between x and y. I can know x is equal to 42, which means I plug that into my area equation, and my maximum area is going to be 882 feet squared. Okay. One last optimization problem that we see every now and then, and this is where we have a parabola, we have a semicircle of y equals the square root of 18 minus x squared. We're trying to find a maximum rectangle in there. I have these two equations. You can see I'm going to plug one equation into the other, which means area equals 2x times the square root of 18 minus x squared. What do I want to do? I want to take this derivative, set it equal to 0. You can do that in your calculator using your solve function, and you will end up finding that x is going to be equal to 3, which means y is going to be equal to 3 if we use my original function, which means the maximum area is going to be 18 right there. Okay, so that is optimization problems. We're basically using the first derivative test. The last thing for Unit 5 that you have to know about is using the mean value theorem of derivatives, which means that we know if we take a look at the slope from A to B, so the slope from this point to this point right here, that slope will be this. There will be another point if it's continuous and if it's differentiable. It will be another point that has the exact same slope at least one point within those 2 points. And so that is the mean value theorem of calculus, which means f prime of c is going to be equal to f of b minus f of a over b over a, which is the slope formula. The slope of the tangent at c is going to be equal to the slope of the secant through a and b. So here's our problem. We want to know when the instantaneous rate of change, that's where f prime of x is equal to 2x minus 2. When is that equal to the average rate of change? So how do I find my average rate of change? I'm going to take a look at f of 0. So I plug in 0 squared minus 2 times 0. That's 0. I'm going to plug in 3. 3 squared minus 2 times 3. That ends up being 3. I take a look at the average rate of change, which is otherwise known as the slope. 3 minus 0 over my x is 3 minus 0. That gives me a slope of 1. So when will that average rate of change equal that instantaneous, that first derivative? Well, we can solve for x, and x is equal to 3/2, and that is where my average rate of change is equal to my instantaneous rate of change. So hopefully that was okay. Unit 5 is a big unit, shows up a lot on the AP Calculus exam, so make sure you go through the sample practice problems and then tune back in the video tomorrow. Thanks, guys. I'll catch you on the flip side. Bye.